Hello everybody, my name is Polina, and today I will be speaking about a neural network model for video-based facial expression recognition on mobile devices. Nowadays, there is a high demand for facial image models, representations, and features that can be used to improve the speed and accuracy of emotion recognition tasks. Existing methods for recognizing facial expressions in videos include temporal classification using dynamic Bayesian networks, spatial classification using support vector machines, multiple kernel learning, deep learning, and others. Although image models trained using the mentioned techniques often perform well on emotion recognition datasets, many of these approaches are ensemble methods that consider other modalities besides video. Moreover, the runtime and space complexities of the best image models are too high for many practical applications. So, in this paper, we propose a new, efficient, and lightweight approach that can be implemented on mobile devices. The task of the paper can be formulated as follows. It is necessary to assign a class label to an input sequence of video frames. For simplicity, we assume that every video clip contains a single person in each frame. Now let's discuss the data that we used for training. In the experimental study, we used the AFEW dataset from the Emotive 2019 challenge, which consists of short video clips extracted from movies. Now on to the proposed approaches and experimental results. The first proposed pipeline is presented on the slide. Since the key information about an emotion is encoded in the facial expression of the observed person, it is necessary to detect a facial region in each frame of a given video using a detector like MTCNN. Then, deep facial features are extracted from every detected facial region. Using common facial descriptors from pre-trained networks such as VGG face, res face, or center face results in considerable computational time and complexity. So, to speed up this step, we used a lightweight multi-output extension of the EfficientNet B0 model and used the output from the penultimate layer of this network to extract 1,280-dimensional feature vectors from every video frame. For feature-level frame aggregation, we use a statistical encoding module. We concatenate the mean, standard deviation, minimum, and maximum of the features over all frames, which produces a single feature vector quadrupled in size that represents the entire video. After that, we apply L2 normalization globally to the resulting video descriptor. Finally, the classification module consists of a linear support vector machine trained using these resulting video descriptors. We have previously conducted experiments to prove our hypothesis that preliminary training of the feature extractor for the recognition of facial attributes such as age, gender, and identity significantly boosts the performance of the emotion recognition task. We have also studied different facial detectors and pre-processing techniques in this pipeline. If you want to learn more about why we use the MTCNN facial detector and the L2 normalization technique, please check out our previous paper. In this paper, we explored different feature extractors and classifiers in more detail. Firstly, we test two different models as feature extractors in the proposed pipeline. The first feature extractor is a lightweight multi-output extension of the MobileNet version 1 model that was pre-trained for identity prediction on the VGG Phase 2 dataset and further fine-tuned for emotion recognition on images on the EFFECTNet dataset. The second model was trained with the same methodology using the EfficientNet B0 architecture. It can be seen from the table on the slide that the EfficientNet feature detector is much more effective than the MobileNet model in all cases. We also looked at different classifiers to be used in the last step of the pipeline. The best accuracy was achieved when using a linear support vector machine. Next, we performed an ablation study to assess the importance of each statistical features in the statistical encoding module of the proposed pipeline. Although the best result was achieved by aggregating all statistical functions, it was discovered that the mean and maximum had the most impact on the accuracy. Using just these two functions in the stat encoding is only 1% less accurate than combining all functions. Therefore, it could be possible to potentially lower the dimensionality of the video descriptors by using only the most significant features. In addition, we examined the effect of principal component analysis on the accuracy. However, in all cases, PCA had little or no increase in accuracy at all. Inspired by frame attention networks, which are designed to adaptively aggregate frame features, we propose a second pipeline, which takes a video with a variable number of frames as an input. The feature embedding module is represented by our efficient net feature extractor, which is the same model that was described in the first pipeline. Next, the input to the attention module is obtained by concatenating the facial feature vectors with the output of the point-wise maximum of these same feature vectors. The resulting vectors are then used by the frame attention module to learn attention weights, which are needed to highlight the most significant frames and adaptively aggregate the frame features to produce a fixed dimension representation of a given video. This pipeline is studied with multiple attention kernels, including single attention, relation attention, and self-attention. In the experimental study, we compare the attention-based approach to recurrent neural networks and study the effect of L2 normalization on the resulting accuracy. We also explore a new way of forming the training and validation sets by concatenating the frame features with an additional vector, which is the output of a statistical function that is calculated over all frames using pointwise operations. A comparative study showed that using the maximum as the statistical function, as well as no L2 normalization in combination with a relation attention kernel, leads to the accuracy of 57.26%. Finally, we compare both proposed approaches to several state-of-the-art emotion recognition methods on the AFEW dataset. The stat-based approach achieves state-of-the-art results on the AFEW 8.0 dataset, beating the baseline from the Emotive 2019 challenge by almost 21%. Furthermore, we were able to improve the accuracy of the frame attention networks approach by 6% by using our efficient net feature extractor and additionally feeding the maximum over all frames to the attention module. The proposed pipeline was implemented in a mobile demo application which can predict the emotion of each person in a given input image or video. Our main contribution consists of the efficient net-based feature extractor that can be used to obtain high-quality representations of input data for the emotion recognition task. Secondly, we proved that the current trend for using the attention mechanism in solutions to many machine learning problems can also be successfully applied to the emotion recognition task. We propose a new way of creating training and validation sets for sequential models, which consists of passing the output of a statistical function along with the facial feature vectors to the network. This technique significantly boosts the performance of attention-based models. Thanks for listening. I'm ready to answer any questions.